of the things that we can do is we can use this information to figure out what the actual energy, the enthalpy of our reaction. So how much heat is transferred in our chemical reaction. We can actually estimate this using bond energies. And the way that we can do that is if we evaluate all of the bonds that are there in our reactants, and we compare that to all the bonds that are there in our product, we can compare the two against each other, and through that comparison say, okay, the bonds in the products have more energy. That energy had to come from somewhere. It must have come from the outside. So the overall energy is positive, which is an endothermic reaction. Or conversely, we can say, hey, the products have less energy than the reactants did, and so they must have released that energy as the reaction proceeded. That's an exothermic process. So what we really get into here is through the bond energies, we can estimate delta H. And the conventions that we've talked about as far as our sign are concerned apply here as well. Breaking bonds requires an input of energy. Input of energy is a positive energy. Breaking or forming bonds is going to release energy. The release of energy comes off as a negative energy. And so when our total reaction has a negative energy, that means that energy has been released from the reaction. We call that an exothermic reaction. When energy has to be brought in to allow the reaction to occur, energy input is positive. That's an endothermic reaction. And so we can calculate this using this equation. And the equation here is that delta H, the enthalpy of reaction, is equal to the sum of all of the bonds that are broken in the reactants and subtract from that all of the bonds that are formed in the products. So what does this have to do with Lewis structures and molecule drawing? Well, in order to know what kinds of bonds are being broken and what kinds of bonds are being formed, we have to know what the molecular structure looks like. And so if we have a reaction like this, we can use it to figure out our bond enthalpy, or excuse me, we can use our table and our structures here to figure out the actual enthalpy of the reaction. So what I like to do in problems like this is I kind of start drawing lines. So here are my reactants. So these would be the bonds broken. And over here are my products. These are the bonds that form. And so I can start doing an accounting of what's there. I have one nitrogen to nitrogen triple bond. And I have 3 hydrogen to hydrogen single bonds. On the product side, I'm making 2 ammonias. Each ammonia has 1, 2, 3 nitrogen to hydrogen single bonds. So on this side, I have 6 nitrogen to hydrogen single bonds. And so to address this, I'm going to go back to that slide that had, and I'm going to look up the values that I need. So the nitrogen to nitrogen triple bond, that was 945 kilojoules. Per mole. And I have 1 mole of nitrogen. Hydrogen to hydrogen single bond, 436 kilojoules. 436 kilojoules per mole. And I have 3 moles of that because I have 3 of those types of bonds. And then finally, nitrogen to hydrogen single bond, 391 kilojoules per mole times 6 moles. So go back now to where I was, start adding together these values. On the reactant side, 945 plus 436 times 3 gives me a grand total of 2,253 kilojoules for the bonds that were broken. On the product side, 391 times 6 gives me 2,346 kilojoules. So delta H for the reaction is going to be 2253 minus 2346, which would be a negative 93 kilojoules. And again, the sig figs for that one, since we are subtracting, the ones place is what is maintained because the ones place is the last digit in each of those values. So we round to the ones place, which gives us our negative 93. All right. Any questions about this example? All right, let's take a look at another one then. In this one, I've got formaldehyde, CH2O, reacting with oxygen to make water and carbon dioxide. Now, before we get into anything else, we got to make sure that this thing's balanced. We've got 1 carbon, 2 hydrogens, 3 oxygens, so we're good. Okay, so what I want you to do, do an evaluation and split it up, figure out what bonds are here, what bonds are here, and what values you need to look up. And so let's take, I'll give you about 90 seconds to figure out what bonds we need to look up. And then for those of you that don't have the table handy, I'll go over to the table and let you look up the values that you need. So go ahead and take about 90 seconds, figure out what bonds are being broken, what bonds are being formed, and take it from there. Okay, so there was a bit of a trick in this one. For whatever reason, the carbon to oxygen double bond in carbon dioxide is different in its energy compared to most other carbon to oxygen bonds. I personally am not sure of the reason, but I do know that that phenomenon exists, and that's why we have a different value, 799, for carbon dioxide compared to the rest of carbon oxygen, which is usually 743. So there is a little bit of a twist in there. There's a little bit of a trick that you have to be able to reconcile in order to get the right answer here. But if you do the calculations otherwise correctly, on the reactant side, you should get 2,067 kilojoules. And on the product side, you should get 2,524 kilojoules, which means that delta H of the reaction, which is the difference of those two, is going to be negative 457 kilojoules. And this does make sense. I mean, compared to the last reaction that we had, combustion reactions are more exothermic. Combustion reactions are generally quite exothermic because we're talking about something catching on fire. And so when formaldehyde catches on fire and produces these products, this is the result, and we get a good bit of heat. And actually, for combustion reactions, is relatively low. We usually see significantly higher than this because there's a lot more carbon and hydrogen to burn.